Swayam Prabha. Digital India. Educated India.
All right, guys, welcome back for the last session that I'm going to cover. So we looked at loop invariants, right, and how to identify loop invariants, how to move them around. Let's look at the impact. See, we got this so far, right? We started with a code which had 3 million index operations and 2 million multiplications. We brought it down to around a million plus multiplications and a million plus index operations. Let's see what all we can do. I mean, just to make you go further, kind of gaga. Let's see. We'll look at what is called a strength reduction in loops. Okay. We know what's the loop induction variable. When I have a loop for I equal to 0, I less than n, I plus plus, that I is called the loop induction variable, right? So in every iteration, it increases. Let us say it increases by 1, okay? I call an expression as an induction expression if that expression looks like this, IC1 plus IC2. It can be reduced to something like IC1 plus IC2. See, we still, despite the one year of online teaching, we still haven't learned that we have to remember to share screen. Okay, so as I was saying, the loop induction variable, let's say it goes from I0, I plus 1, I0 plus 1, I0 plus 2, and we say induction expression as something of the form IC1 plus IC2. That way, in the first iteration, it is I0 C1 plus C2. Second iteration, I0 plus 1 times C1 plus C2. Third iteration, I0 plus 2 times C1 plus C2. Okay? If you have any such induction expression, I can do further optimizations. What can I do? Wherever this IC1 plus C2 occurs in the loop, I'll replace it with a temporary T. Okay? So let us say I have a loop over some loop induction variable I. And I have code that looks like this, IC1 plus C2. Okay? Let's say I'm writing something simple, x equal to this. Okay? I want to replace it with T equal to I0 C1 plus C2 and x equal to T. And at the end of the loop, T equal to T plus C1. What did I do? See, one point to note, if you look at the value of x, initially it is this. Next it is this. Next it is this. What's the difference between the two consecutive updates to x? It is C1. Correct? It increases by C1. So what did I do? I said T equal to this, x equal to T, and T equal to T plus C1. Okay? What did I gain from this? Can someone point it to me? Between this code, let us say this loop goes over 100 iterations. How many multiplications do I have?
100 multiplications and 100 addition.
Very good. Here, how many multiplications do I have?
0.
Only one multiplication here.
Only one.
How many additions do I have?
100.
100 plus 1. 101. Right? So I replaced 100 multiplications and 100 additions with 101 additions. And as you know, additions are much cheaper than multiplications.
Multiplication.
Right? So this is strength. This is called strength reduction. What did I do? I took an expensive operation and then replaced it with a cheaper operation. Okay. Now let's look at our code that we had at hand. Yeah, let's look at this code. Let's look at this code. Yeah, go ahead. There's a question.
I had a question now. I mean, your statement that you made earlier that multiplication is cheaper than addition.
Typically.
Yeah, is it really true today in today's?
Yes, as of today it is in the popular machines, in the common machines that are available.
Okay, because with the advent of this one, right? I mean, multiply and accumulate and all are.
Yeah. Multiplication is much more expensive. You do a lot more operations.
Okay.
Okay.
Okay. Yeah.
Fine. Further, if you look at it, here I'm doing 100 plus 100. Here I'm doing only 100 in the loop plus 1. So the number of operations are also less. Okay. Fine, Samir?
Yeah. Yes. Because
Okay.
I mean, indirectly, right? I mean, from my experience, I mean, multiply and accumulate is normally is the same, and adding a single cycle extra will actually cause probably end up taking more cycles, and so 101 could be higher than 100. So
No, it's not 100. It's 200, right? It's 100 plus 100.
yeah, I mean, assuming that multiply and accumulate is kind of a single this one nowadays, so that's the reason.
No. So when you look at multiply and accumulate, typically the addition there is, this is not a single instruction. The CISC instructions can be big, right?
Understood. Yeah.
So the moral of the story, I guess, what I'm trying to bring out is that, look, in general, multiplication is expensive. You can using a more fancy instruction, you may reduce it from 100 plus 100, 100 multiplication plus 100 addition to something less than that. But still, 100 additions is much cheaper.
Understood. Yeah, that makes sense. Yes.
Okay. Fine. Let's continue. So if we go back to this particular loop, do you see any code where I can do strength reduction? Do I have any induction expressions that we talked about? Is there any induction expression? Just look at this loop. If you look at t times k, what do you see? What is the value of this expression when k equal to 1?
T.
T. K equal to 2?
2t. So
2t. So what I can do, I can write a temporary, let's say T4. I can write here T4 equal to T. T4 equal to T. And here I can replace it with T4. At the end of the loop here, I can write T4 equal to T4 plus K. So now tell me how many multiplications do I have? This whole 1 million multiplications are gone.
Right.
Similarly, do you see any other thing I can do in this loop?
The I is constant.
The I times j. Even this can go out. I can make here T5 equal to I. Replace this with T5. At the end of the loop, here I'll write T5 equal to T5 plus I. How many multiplications do I have now? From 2 million multiplications, it came down to 0. How cool is that?
Yeah.
Any questions? Okay, wait, yeah, let's wait. Are there any questions on this? No?
No.
Very good. Let's go further, okay? Let's again come back to this, the first for loop we looked at. Let me just clear the board a bit. Let's look at this for loop. To which address am I writing here in iteration 1? Aditi, to which address am I writing at k equal to 1? Harisha or Hanisha? Hanisha, sorry. Hanisha. Sindur. Anyone wants to answer this? To which address am I writing here?
T1.
Address of T1 of 1. In the next iteration, what will I write to?
T1 of 2.
Very good. Address of T1 of 2, right? At this address I'll write. Can I do something like this now? Let me write. So let me take a temporary T6 equal to address of T11. Okay? And this I will write it as star T6 equal to this. And then and then in the loop what I will do? T6 plus plus. So in the loop, how many array index operations did I do? In the loop, how many array index operations am I doing?
0.
0. From a million array index operations, it became 0. And why am I doing T6 plus plus here? Can someone explain?
To access the next address in
Exactly, so that I can go to the next pointer, right? I can do the same thing for T3 and A sub I, and I'll have some code like this. Okay, I will have a code where I'm only reading the address once here, and then I'm incrementing the address. But remember, when I have to increment the address, I have to be slightly more. I have to do this plus plus. Wait, I think, yeah, it looks like this, right? I'm incrementing the address here. For the outer loop, I will increment the address by 100. For the outermost loop, I'll increment the address by 10,000. Because if my array A is an array of 100 cross 100 cross 100 array, then when I do A sub I and A sub I plus 1, the difference between the addresses is 100 times 100. So I'm adding this. And between A sub I and between A sub ij and A sub ij plus 1, the difference is 100 elements. So here the difference is 1000 elements, 10,000 elements. It's 100 elements. So I'm doing T7 equal to T7 plus 1. And we have already seen this one plus 1. Now tell me one thing, guys. How many index operations do I have in this code? 0. How many multiplications do I have? 0. Do you remember the original code which had so many multiplications, so many index operations? Does this really make you feel, wow, can a compiler do this?
Yeah, definitely.
Sir, but you are still dereferencing the pointer, right? That's the same thing as an array access.
No, it's not. So this one is a simple load. This will be replaced with a simple load. Array this thing, I have to do this array sub I, right? So that's an indexed load.
Yeah.
And if I am doing a sub I sub j, that's kind of, I'm getting a sub I, then sub j, then sub k. Right?
Right.
And if a is a pointer, then first of all you have to dereference a, then a sub I.
Right. Okay. Yeah.
So the fun point here is the compiler has figured out that there is actually some common pattern I have found, and using that it has optimized these things away. Okay? Questions? Do any one of you feel that this is still wrong or something of that sort? Okay. Let me just check randomly if there are any questions. Yeah, Aditi, you have a question?
Sir, what is copy propagation? The last statement.
Yeah, I'll come to that. There is one optimization called copy propagation. What it does is that if it sees that the same variable is used at multiple places, it can kind of improve, it can kind of eliminate some variables and all that. We haven't covered copy propagation in this session, but it will be covered hopefully later. So at that time, I want you to come back to this example and see how copy propagation can further improve this code. Okay, so this is like a future task. Okay. Abhinav Garg, are we fine?
Yeah, yes, sir.
Good. What about Vikram Kumar? Vishal Pai? Any questions? Vishal? Okay. All right, let's continue then, if there are no questions. So what we will do now, see, we looked at a couple of loop optimizations already. Loop unrolling we did, loop invariant code motion we did. I will not spend so much time explaining the beauty of all these, but I'll still go over all of them because I feel they are simple. Now that you have seen two optimizations in depth, you will be able to appreciate many of them without too much difficulty. Okay? Let us say I have a loop that looks like this. Okay? And in this S, the variable V is not modified, or this condition is not changing in the S. You know what I can do? I can take this code and replace it with if V. What's the difference between this and this in terms of performance? Anyone?
The branch is only executed once.
The condition is only executed once, right? So this is a far better code, far improved code than this. So now the question is, when can you do this transformation? Can someone tell when can I move it around, move it out?
If the value of V isn't really affected by the loop, what happens in the loop?
Yeah. V is loop invariant. Okay. V is not dependent on what S does or what I does. Okay. Or I'll write it as instead of writing loop invariant, I'll write it as V is not dependent on S or I. Okay? Now, is it equivalent, this guy and this guy? Or is there something more missing? Let me give you a hint. One minor thing is missing. Can someone point it out?
Can it have the same exception problem as before?
No, so there's no code here, right? There is absolutely no code here. This is the pattern for header if vs. That's it. That's the pattern. So if inside S, if there is an exception, fine. The exception is thrown. Even it will be thrown here, it will also be thrown here. No difference.
No, but V might throw an exception evaluating.
No, V is not an V is okay. V is not dependent. Okay, V. I wrote V as a variable, but if you want to see V as a expression, then we should say V has no side effects. Right? Because what we said is V was a variable, but if you see it as an expression, then we want to see that V has no side effects. But for us, V is a simple variable. Okay, just a condition variable. If it is an expression, I will first do loop invariant code motion, move that expression out, and then see if I get this form. If I get this form, I'll translate it to this form. Okay, my question is back. Is it equivalent? Code A and code B, is it equivalent? I'm claiming code B is missing something.
Sir, in first option, maybe if is checking every time at every iteration.
Yeah. Fine, but here it's better, right? Here it's like the condition doesn't change.
Oh, so in the first, the value of I will change in the second.
Perfect. Who said it? Aman, is it?
Yes, yes.
Very good, Aman. Where are you from, Aman?
I'm NVIDIA employee. I'm working at NVIDIA.
All right. NVIDIA has good employees. All right. So what am I writing here now? So what I will do, see at the end of the loop, what is the value of I? Aman?
In the second one,
No, at the end of the loop, what should be the value of I?
in the first loop, it would be n, because
No.
the loop would,
N plus 1 you mean.
yeah, n plus 1, yeah.
So what I will do, I will rewrite this code if V from here to here, and outside the for loop, I have I equal to n plus 1.
Yeah, yeah.
Make sense? All of you? Okay. Let's see, Vikram, are we fine?
Yes, sir.
Okay, good. Let's continue. So we looked at loop unswitching. We will look at one more optimization called loop tiling. So this is done. This is done. Loop tiling. Let us say I have a loop that looks like this. And I have some code that goes over A sub ij, like this matrix multiplication, something that repeatedly accesses A sub ij. Okay. Maybe a matrix multiplication where I kind of repeatedly access the rows again and again, repeatedly access the columns again and again. So if I have a matrix like this, I repeatedly access these elements again and again. So what loop tiling does is the following. It says, let me do this. Let's make it M and N, make it more general. M by some D. So I goes from 1, I goes to M with increments of D. Okay. So, and similarly for J goes from 1 up to N with increments of D. And I'll make this one outer one, let's say. Maybe I should make it II and this one JJ. For I equal to. So what I'm doing, I'm jumping I equal to 1 here, J equal to 1 here. Next, I equal to 1, J equal to a jump. Okay. So what I'm basically doing is for I equal to 1, my JJ varies from 1, 2, 3 up to here. Okay. Then I will go to the next side. So basically I want to do this block first, then this block, then this block, then this block, then this block, then this block. So for this I am writing I equal to II. Let us write the exact expression. II times zero index would have been easier here. Fine. Let's see. So first time it should go from 1 to D. II minus 1 times D plus 1 to II times D. Okay. Okay. So I goes from II minus 1 times D plus 1 up to II times D. Similarly, the J loop I'm writing here. For J varies from JJ minus 1 times D plus 1 up to JJ times D. And then the statement, whatever, the same statement remains here. If this is the statement S, same statement S. So what did I do? I took a loop which is going over the complete array like this. Now I change it to this, then I go up, then one more block, then again go up, one more block, then come to the next row. Again block, go, again block, go, again block, go. This is called as loop tiling or loop blocking. If these elements are accessed again and again, if I choose the tile size carefully, for the full time when I need these elements, they are always there in the cache. Okay. So what did I do in loop tiling? I took this loop, this two-dimensional loop, I made it a loop nest with four level depth. Okay. The complexity hasn't changed, just that the cache behavior has improved because whatever these elements which are required, they're all gotten once. I keep them once and keep on reusing them. So that whole block is used once. I'm working one block at a time. Okay. So this is called loop tiling. So loop tiling helps in improving the cache accesses. Any questions in this? So instead of going from 1 to 100, I'm going now, let us say, outer loop. Let's say let not make it 100, let me make it 64. That will be easy for me. If I have a loop like this, I'm transforming it, let us say, 1 to 64 in a blocks of 4. 1 to 64 in a block of 4. Then 1 to 4, 1 to 4. Okay, so the innermost block is a 4 cross. It will access this 4 cross 4 blocks. Does it make sense?
Sir, if a compiler does this optimization, how does it choose the block size? Because it will probably depend on the cache.
Absolutely. Who asked this question? Rupanshu, is it?
Yes.
Very good, Rupanshu. The block size tightly depends upon the data cache size. So if I have a data cache that can hold some X number of elements, I will choose a block such that the elements accessed in that block are fully available in the cache or and fit in the cache. Okay? So the compiler is aware of the hardware. So this is a classic example where the compiler does, this is a high-level optimization of sorts, loop tiling, or mid-level, but which is clearly dependent on the hardware features. Okay?
Right.
Very good. So now let's ask this question, when can I do this? For this to be done, remember, after I have done this transformation, the order of the execution has changed. So this can be done only when different in different iterations, let's say S11 and S12, S13, S14, S21, S22, S23, S25, all of them, they are all independent. So this can be done only if all the iterations are independent. See, I'm unfortunately, for lack of time, I'm not covering the dependence analysis. But remember, there is a serious, a very important chapter called dependence analysis, which will tell us whether in different iterations, this body will have dependence with another iteration. Iteration I equal to 1, j equal to 1, does it have dependence on I equal to 3, j equal to 5, things like that. Okay. So we will do dependence analysis to figure out that different iterations, in different iterations, S is independent of each other. So we need S, different instances of S have to be independent. Only then we can do loop tiling. Okay? Any questions? Okay, I will go over one more cool transformation before I. I'm very excited about this. This thing. I mean, these things can give you same looking code, same complexity, but it can really change the behavior of the execution. The executable. Okay, let's look at one more code. So far, we are looking at for loops, right? Let's look at a while loop. While condition S. Okay. If we generate the code. Oh yes, thank you. So Ramakrishna mentioned the dependence analysis will in detail be covered by Professor Sanjay. Perfect, perfect. With more powerful analysis called polyhedral analysis. Perfect. Okay, we have a while loop here. When we generate code for this, how does it look like? It checks if condition go to L1, or rather if not condition go to L1, S go to L0, this is L1. Correct? Is everyone clear that this while loop gets translated to a code like this? Any questions? No, Vishnu, in the loop unrolling, we have not changed the complexity of the algorithm at all. It still does the same number of iterations. Just that the cache behavior is better. Okay, let's come back to this. Any questions from here to here? Any doubts that these two are equivalent? Shambho Roy? Venkatakirti? Okay, so this is equivalent, right? So for every iteration, how many jumps am I doing, or how many conditional or unconditional branches am I encountering in every iteration? In every iteration, I have one conditional jump and one unconditional jump. Correct? Let me rewrite the code. I'll rewrite this while loop to a do while loop. What's the difference between a while loop and a do while loop?
Do while is always executed at least once.
Execute at least once. So what I will do the following. If condition S or rather, sorry, if condition
It's not visible.
it's not visible?
Yeah, now it has come.
Okay, yeah. So now what did I do? I replaced this while loop with this code, if and do while. Do you see that they are equivalent? Now look at the code that is generated for this. If not condition, go to L1, L0, S. If condition, go to L0, L1. Now in every iteration, how many jumps do I have? Conditional, how many conditional or unconditional jumps? Anyone? This is the loop, right? Only one. I had two here. So I replaced the number, the conditional jumps and the jumps to only one. There is only one conditional jump here. So this is called as loop inversion. What did I do? I took a while loop and replaced with a do while loop. Any questions? Sudhakar Kumar?
No, sir.
All right. So you see, we write these while loops, do while loops, without, probably we don't realize that one of them is more efficient than the other. Which is more efficient between while and do while?
Do while.
Do while. So in case you happen to write a while loop, the compiler does take care of it and replace it with a do while. Okay. Any questions so far? No? Okay, then we'll do one thing. We will take a small pause here from loop optimization. There are a few more that are interesting I have listed here, but considering the time, I will go into function optimizations, a couple of them, and come back to it if possible. Any questions on loop optimization so far? No, right? Okay.